Good morning, all of you. Shubham Jane. Hope you are having good times at home with your family and friends. For day 5. Some of our student friends asked for numericals based on the concepts that we have cleared during past few days. So today's class will do numerical examples on few models, and let me tell you, most of the calculation 70% I will do, and I will leave it 30% for simple simplifications and calculations. Hope you will do that, right? Now let us come to first example. Here I have shown a system of charges. 3 discrete charges I have shown at the 3 corners of an equilateral triangle. This is an equilateral triangle ABC, G is the centroid. Now the question is, find the net potential at G, find net intensity at G. Right. Look at this solution. First, about the geometry, it is all the sides AB, BC, CA, same, equilateral triangle L. And then I have given the distance of the centroid from each of the corners. From each of the corners, AG, BG, CG will be the same. And you know pretty well that will be L by root 3 if I take it as small r. So I will use small r, L by root 3. Now let us write the potential at G. Remember, potential, scalar quantity, net potential at a point is algebraic sum of individual potentials. Now potential at G is due to this charge Q at a distance R, also the charge at B, the one Q, distance the same R, and again here you have another charge. I have minus 2Q taken, right? Therefore V at G is, use the same expression, potential due to point charge 1 by 4 pi epsilon naught Q by R. So here comes 1 by 4 pi epsilon naught, this Q by R, this one is positive. Again potential due to this charge 1 by 4 pi epsilon naught Q by R, the second term, and look at this third term plus 1 by 4 pi epsilon naught minus 2Q by R. Remember I told you in examples of potential, any sign given to the charge will be carried into the calculation. That is where I have substituted with, along with negative sign, you will find that this turns out to be 0, right? Now look at the figure one more time. We have a complete symmetry like equilateral triangle, and the given point is also point of symmetry. Therefore in the case of any symmetric geometry and potential, net potential asked at the point of symmetry, it will always be 0 when algebraic sum of the charges is 0. Now you calculate here Q plus Q minus 2Q, the net charge is 0, and hence the net potential at the point of symmetry is 0. This you can use it for any symmetric distribution of charges. Now let us come to the intensity calculation. If I have to calculate the net intensity at the point G, remember field is a vector quantity. To find the net intensity, it is not algebraic addition, vector addition. So that is why, look at this vector diagram. The G center of centroid I have taken. This is what is, this Q produces intensity which is E1. The second intensity at G is due to the charge at A, E2 bar, E1 bar, E2 bar, E3 bar, and now what is E3 bar? You can see that is the intensity due to the charge minus 2Q at C, and of course you should remember the point charge intensity is always away from positive charge than it is towards charge. Therefore these are the arrows, you can find these vectors, and E3 bar is towards C because of the negative charge. Now 3 vectors added. For that, first I have taken these 2 vectors, see, E1 bar and E2 bar, same charge, same distance, magnitudes same, and what is the expression? 1 by 4 pi epsilon naught Q by R square. You can see here the substitution, and now this is equilateral triangle. This angle between these two vectors will be 120 degrees, right? So theta between E1 bar and E2 bar is 120. Now what is the resultant of E1 bar plus E2 bar? A very famous formula, root of p square plus 2 square plus 2pq cos theta. You can see here substitution. E square plus E square, 2E square cos 120, cos 20 minus 1 by 2. Substitute, you will get the answer as E. Therefore, E1 bar and E2 bar will have their magnitudes, and their resultant is magnitude of E. And now look here about E3. This is what is E3 due to the charge minus 2q. Once again, 1 by 4 pi epsilon naught. The charge is 2q and L by root 3 whole square. The difference between these two terms you will see. This is q term and this is 2q term. Therefore, E3 is nothing but 2E. If I take E1 and E2, the magnitude as E, the magnitude of E3 bar will be 2E. And what you find from the symmetry, this vector E3 bar is parallel to the resultant of E1 bar and E2 bar. See here, E1 bar and E2 bar, this is the resultant, and E3 bar is parallel. You can find this, right? So now these are two vectors parallel. Therefore now finally I am writing the net intensity at the centroid EG is parallel vectors are always added. Anti-parallel vectors you will use minus sign. Therefore here EG is mod E3 bar plus mod E1 bar plus E2 bar. So this is 2E and this is E. So final answer, the net intensity at the centroid is 3. Okay, in the same example, supposing a small change is given. What is that small change? Now I say, instead I will write here a charge capital Q at C, and the new question now is, hope you got this one. Now I have a small change in the same question. Supposing I say C vertex occupies a charge Q. Now the question is, for what value of Q potential at G is 0. Same question but asked in a different way. For that the answer I have told you earlier, any symmetric geometry, at the point of symmetry net potential is 0. When the algebraic sum of the charges is 0. Therefore here Q plus Q to Q, this capital Q should be minus 2Q, because for that only the net charge of the system becomes 0. How do you get this one? You want me to show that? So this is Q plus capital Q is equal to 0. Net charge of the system 0, and therefore the answer Q is equal to minus 2Q, like that. Supposing in the same question, if I say for what value of Q the intensity at G becomes 0. See, earlier we have taken for what value of Q potential at Z becomes 0, but now this time it is 1. What value of Q the intensity at centroid becomes 0. Now for that again, look at this vector diagram. Earlier we have taken E1 bar and E2 bar. The magnitude is E, right? And these are two positive charges and away. Now this E gets cancelled. Look at this. Supposing this is what is the magnitude E1 bar and E2 bar, the vectors. For now the resultant to be 0, a very simple common sense point using the vector addition should be, now the third intensity should be directed like this. Got the point? Third vector should be directed in this direction, so that these two vectors will give, this is what is E1 bar plus E2 bar. This vector is E3 bar. Now what will be the condition for the net field to be 0? Now I am writing mod E3 bar is equal to mod E1 bar plus mod E2 bar. Therefore E3 is equal to E, because already we have calculated mod E1 bar plus E2 bar equal to E. We have shown that, right? I am using here. So mod E3 bar should be equal to E. But please do remember, for that to happen, now 1 by 4 pi epsilon naught capital Q by L by root 3 whole square all equal to 1 by 4 pi epsilon naught. Here you have taken E. Remember the same I am writing L by root 3 whole square. E value here you can already have shown this, right? So this is what a simple result giving. You can cancel all the common terms on either side. What you will find is Q is equal to Q. But please remember this capital Q is equal to plus Q this time. Why? Because here you see this E3 earlier you have shown towards C because of the negative sign towards the charge. But for this vector to be away from C, this should be a positive charge. Capital Q is equal to plus Q. Then E at G, this vector becomes a null vector. Like that. So every example, number of times we have shown in the class that each example make a small changes, you will find good number of new examples. Right? You got it? One more example. This time here, again we'll do example relating potential and field. Now this is the given data. A and B are two shells, two conducting shells of radius A and B with charges Q1 and Q2. Or let me write QA and QB, the charges initially are there. Now the question is that supposing if they are connected by a conducting wire, what will be the ratio of their final intensities is the question that I am framing. So finally the question is, what is the ratio of their final intensities, that is after connecting by a wire. After this, we'll improvise the example and we'll show it as a different 2 to 3 types of example. Now here, when conducting shells are connected by a wire, what happens? Earlier we have told, potential is such a term in electrostatics that determines the flow of charges from higher potential to lower potential. Similar to the one we did it in thermodynamics from higher temperature to lower temperature until both acquire common temperature. Use the same kind of principle here. Then depending upon, remember here the flow of charges not determined by the quantity of the charge. Higher charge to lower charge never takes place. Always from higher potential to lower potential. Nothing to do with the charge, nothing to do with the size. It's always potential that determines the direction of flow of charge. Therefore here, when we are connecting, there will be flow of charge. I don't say from A to B or B to A right now, we'll do it in the latter course. Now charge flows such that both acquire a common potential. Initially, it was VA, now it becomes VA dash after connecting. Similarly, the potential of B becomes VB dash. Now look at this, it is the same potential that is acquired by the two shells. Until then, the flow of charge will take place. This is the what is common potential. Now here you see, you remember the expression due to potential due to shell we have taken on the surface. V is equal to 1 by 4 epsilon Q by R. So V proportional to Q by R. Now here, since VA dash by VB dash is equal to 1, use this V proportional to Q by R. What do you get? QA dash, the new charge on the A by the new charge on the B. Potential getting changed, even charge on the shells becoming different. So QA dash, the new force on A, new charge on A, and QB dash, the new charge on B, equal to. Now since B is same, Q proportional to R. QA dash by QB dash is RA by RB. One relation you got. Remember this relation. Remember this relation. Now, the question that is asked is, what is the ratio of intensities after they are connected by a wire? After connected by a wire. Now here you will see what is the new intensity EA dash 1 by 4 pi epsilon naught Q by R square. Remember spherical shell intensity surface point. The same I am writing here 1 by 4 pi epsilon naught QA by RA square. And EB dash 1 by 4 pi epsilon naught QB dash RB square. Now I want the ratio. I have taken the ratio. See here. The ratio. Now here what is that QA prime by QB prime? Now we have this result RA by RB. Substitute. Got your answer. Now this is what is the ratio. EA prime by EB prime is equal to RB by RA is the ratio of intensities, final intensities after they are connected by a wire. See, the same example, here we will have a small change. What is that? Now, for that, what is the quantity of charge that flows through the wire? Quantity of charge that flows. You are asked to calculate quantity of the charge that flows. Previous example, whatever solution I have started with, I will use that, the same, to find the quantity of charge that flows. To find out this, first you have to compare the ratio Q by R. You have to compare the ratio Q by R of A and B. Supposing here I say this is 5 centimeter and this is 3 centimeter, and I give the values as 6 microcoulomb and this one is 4 microcoulomb is the data. Now what is that Q by R? Why we are taking Q by R? Because V proportional to Q by R, right? And that is when now I am taking this ratio Q by R. So Q by R of A you calculate, how much you get? 6 upon 5, and here you will get it as 4 upon 3. Certainly 6 by 5 less than 4 by 3. So it means that in the given data, according to the given data, this one is at lower potential and this one is at higher potential. Therefore, now the charge flow is from B to A. How you got it? Again, I am repeating. You have to take this ratio Q by R. Higher Q by R will be at higher potential. So that is why now the charge is from B to A. Now, earlier we have got this relation. You remember QA prime by QB prime is equal to, you got it as RA by RB. Already this one is the result. Now I am making use of that. Therefore now this total charge, what was the initial total charge? QA plus QB was the total initial charge. Now we have a principle, that law of conservation of charge without any exception in the nature, and that is why now the new charge QA prime, how do you get? Because this is, now you have a result. QA dash by QB dash is RA by RB. So QA dash is total charge QA plus QB. In this total charge, A should have RA parts. Out of total, RA plus RB. Well, now we want you to substitute. See here, QA plus QB, the total charge is 10 microcoulomb, and RA it is 5 centimeter. RA plus RB it is 8 centimeter. So this is 50 by 8. Yes, 6.25 microcoulomb. So what you have observed is QA prime is 6.25. So earlier it was 6 microcoulomb because charge is flowing from B to A, higher potential to lower potential. So 6 becoming 6.25, it means that the quantity of charge now flows through the wire is nothing but QA prime minus QA 0.25 microcoulomb is the charge that flows through the wire. Interesting, one more example. This time we have given a geometry. You can look and see here. ABCD is a square, I said, a square geometry with a charge of 3 microcoulomb, I say positive charge 3 microcoulomb placed at the corner B. And the question is, another charge 2√2 microcoulomb. And this again, suppose a positive charge. This again a positive charge. This I take capital Q and this I take supposing small q. Now capital B corner occupies a charge of capital Q, and now another point charge small q magnitude is given. Now he says it is displaced from either A to D, from corner A to corner D, or from the corner A to the corner C, anything like that. Even it can be another example like it is displaced from A to B and then D to C. So 3 different ways of displacing the charge small q, and in each of the case calculate the work done. See, this is a very comprehensive question where we will use 2 to 3 concepts that we have learned in earlier classes. The very first one you remember, I have told you by defining the potential, any electric field, the concept of work, use W is equal to VQ. W the work done, V the potential difference, Q is the charge which is displaced. So you can see here I am writing W from A to D. W from A to D is VD minus VA times Q. Here I have calculated potential due to point charge at a given distance. One expression we are using K 1 by 4 pi epsilon Q by R. See here 1 by 4 pi epsilon it is common, Q is also common. So this is 10, and therefore this distance, the diagonal becomes 10√2, diagonal of a square. If it is 1 by 10 minus 1 by 10√2 into small q. Now I am substituting all the values. Simplification should be your job. So this is 1 by 4 pi epsilon 9 into 10 raised 9. Q, the charge at B, 3 micro, and the small q is 2√2 micro. And remember, this is 1 by 10 minus 1 by 10√2. All that is given in centimeter. Therefore, again I have converted it to meters. Here you will see that 10 raised minus 2, 10 raised minus 2, right? Now why this negative sign here you see here? This is 1 by 10 minus 1 by 10√2. This turns out to be negative. It has significance here. What is the significance? Now when you look at this A and D point, you will find that A is at higher potential because of lesser distance, D is at higher potential. And one more time, just rebrush your conceptual topics that you have discussed in the previous classes. Positive charge, the natural direction is from higher potential to lower potential. In such cases, work will be positive. Natural direction, positive charge, higher potential to lower potential, work is positive. Lower potential to higher potential, a positive charge, displacement, work will be negative. Similarly, for negative charge, the natural direction is from lower potential to higher potential. In such a displacement, work is positive. Whereas for negative charge displaced from higher potential to lower potential, work will be negative. So while options are given, you will have both these positive and negative values. You should have a very clear concept about that, and that is why here the work is coming to be negative. Final answer you will see 5.4 times 0.41. You can calculate nearly, it will be greater than some minus, of course, 1.3 something joule you will get. Is it not? So what is the definition that we have used? W is equal to potential difference into the charge that is displaced. And as I have told you, be careful about the charges, which charge is placed and which charge is displacing, whether it is from higher potential to lower potential or lower potential to higher potential. Now I hope this second case, A to C, you only will easily do. Now in this data, A is at a distance of 10 centimeter from the corner B. Similarly, C is also at the same distance of 10 centimeter. Equidistant points means the equipotential points, that is VA or VC minus VD. Next time what happens? It is from A to C. You write it as VC minus VA times. Now here in this case, VC minus VA will be 0 and hence work done will be 0. Again a property of equipotential surface or equipotential points. No work is done in displacing a charge. Now in the same example, if the questioning is if it is a displacement from A to D and then D to C. Remember, electric field is a conservative field. And what is the property of conservative field? In the case of conservative field, work done is always independent of path, depends only on the initial position and final position. Therefore, whether the charged molecule displaced from A to C directly or A to C via the point D or any other path, the work done will be the same. In this case, initially WAC is 0. Even in the third case, when it is displaced from A to D and then from D to C, also work done is 0. So here 3 to 4 points are used, and therefore carefully observe this example and brush up your concepts. See this example. Example says A and B are two concentric shells. A and B are two concentric shells and both are charged. Charge and A is QA. I am not giving numerical value. I am giving you the symbol. If numerical value is given, you can do the calculation as well. So A and B are concentric shells. O is the common center. Here I am showing small a, small b for radii. Now P is a point at a distance C. So everything is that done. Now the question is, you are asked to find what is the net potential at the point O. What is the net potential at the point P, or even what is the potential difference between the two shells. Now one more time, we are using charged shell and try to recapitulate the simple expressions that we have given you yesterday, right? Now look at this point O. Again, V at O will be due to potential due to A and also potential due to B. You will find here. Remember, potential is a scalar and it is always scalar addition. At the same, also remember when you are substituting the numerical values, the positive and the negative signs will carry. Don't forget that. Potential due to positive charge is positive, potential due to negative charge is negative. So now V at O is V potential due to A, and this O happens to be the inside point. Therefore I have taken potential due to dA at inside point, and also O is the inside point for the shell B as well. Therefore it is VB potential due to B inside point. And of course inside point potential same at all points and same as potential on the surface was the result that we have discussed. Therefore it is 1 by 4 pi epsilon naught charge on the shell by radius. Use that expression here. So that 1 by 4 pi epsilon naught is a common term I have taken. So QA by RA plus QB by RB, because both are inside. For both shells, O happens to be the inside point. Therefore, answer is 1 by 4 pi epsilon naught QA by small a, because we have given the symbols. QB by B will be the potential at O. Now, if numerical values are given, you can do the substitution. Supposing the same example says, the same data is given and he says potential at the common center O is 0. Then what will be the charges, ratios of charges or ratio of radii like that. Now here if you substitute VO equals 0, I am discussing this as another question. In the case you are given O happens to be 0 potential point, then what are the different conditions that we can deduce? If this happens to be 0, then what do you get? QA by A plus QB by B is equal to 0. 0. Therefore, what is the answer? You will get it as QA by QB is minus of A by B. Minus of A by B. That negative sign shows that the shells should possess opposite charges, unlike charges like that. So, either calculating the net potential at the common center or ask it in different way like 0 potential point and the condition. Now, next time, let us take the point P. So I am writing at the point P. Again at the point P, the potential will be due to the shell A and as well as shell B. Again, look at that figure and now this expression, potential due to A, but P happens to be an outside point. Therefore, VA outside plus for B it is inside point because P is well inside the shell B. Therefore, it is VB again due to the inside point. Therefore, one more time, 1 by 4 pi epsilon naught, the common QA by R. Remember, potential due to a shell at outside point, yesterday we had taken K, 1 by 4 pi epsilon naught, charge on the shell by R, which is the distance of the outside point from the center. Right? Note should be with you. One more time, look at it. So, this is QA by R plus QB by RB, same inside point potential. And I have substituted here. This R given delta says C and RB is equal to B. Therefore, this is the net potential at the point P. Now, we'll extend this example. Instead of asking potential at common center, instead of asking potential at the point P, suppose if it is asked, what is the potential difference between the concentric shells? Look at this. Now, let me consider A itself as a point on the inner shell, B itself as a point on the outer shell. Now, what here I do? I want the potential difference. Therefore, initially I will calculate potential on the surface of A and potential on the surface of B as we did earlier. Now, I hope you will now do along with me. Now, look at this point A. A is a surface point for the inner shell and A point happens to be the inside point for the shell B, outer shell, right? Therefore, VA, what do you write? Potential V, yes, potential due to potential due to A on the surface plus potential due to B inside point. Then expression, I am taking 1 by 4 pi epsilon naught as common. Therefore, it will be QA by RA surface point plus QB by RB inside point for B. Right? So, this is V at A, the total potential at any point on the inner shell. Similarly, now shall we calculate potential at the point B? That point B I have considered as a point on the surface of the outer shell. Now what happens? Here again, this potential due to A, but the point B happens to be outside point plus potential due to the outer shell B, which happens to be the surface point. I hope you understood these meaning of these symbols. O for outside point, S for surface point, I for inside point, like that. So one more time, saying 1 by 4 pi epsilon naught. Now for A it is outside point. Remember, it is outside point, therefore I will take the distance of the outside point from the common center, which happens to be, yes, look here, this is B, outside point for A, therefore I will write the distance from the common center, which is B. And plus QB on the surface, remember KQ by capital R, radius of B is small b and A. Let me write, okay, this is what is RB and this is what is again RB, both are RB terms here. Because B is at a distance RB from the center, common center with respect to A, and therefore this is QA by R. Now we should calculate what is that VA minus VB. VA minus VB. What is the term you will see? This is QA by RA term. And here there is no QA by RA term. But look at here. QB by RB and this is QB by RB. A common term. When you are taking the subtraction, this QB by RB term gets cancelled. Therefore, what is the result? Hope you can do calculation on your own. See, this is a common term in both the terms. And subtraction gets cancelled. So what is VA minus VB? This is 1 by 4 pi epsilon naught. Here the term is QA by RA minus the second term. Here again you will find QA by RB. This QB by RB term vanishing. So this is what is the potential difference that you are getting. And it has some interesting result as well. Look at this final expression. This is the potential difference between the concentric shells, and it does not contain the term QB. It has containing the term only QA. Now according to the given data that I have shown, QB is the charge on the outer shell and QA is the charge on the inner shell. Therefore, in the case of charged concentric shells, potential difference between the concentric shells is independent of charge on the outer shell. It depends only on the charge on the inner shell. Supposing examples are given in which initially there are some charges on A and B with potential difference, supposing some 1000 volt. Now I will change the charge on the outer shell. And the question is asked, what is the new potential difference? Now answer, you are telling I know the same, because concentric shells, charged concentric shells, PD does not depend on the charge on the outer shell. But remember, it depends upon charge on the inner shell. Likewise, so in this data, we can do 3 to 4 different types of questions, right? Watch it carefully. Example for the case of a dipole, and again using the concepts of field and the potential. Now here, this example says that P is an axial point of a dipole. First, I am reading you the data. P is an axial point for a dipole at which potential is 100 volt and the intensity at the point P is 250 volt per meter. This is the data. Now the question is asked like this: if the dipole is turned by 90 degrees, either clockwise or anti-clockwise. Dipole turned by 90 degrees, what will be the new intensity and what will be the new potential at the same point P? Right? Shall we do that? Now it is the initial case. P is an axial point of a dipole. Now for this, I am doing the rotation. In fact, you also keep writing that this is positive charge and negative charge axial point P. Now I am rotating, turning the dipole. Supposing I am doing it in clockwise direction. So dipole is turned clockwise direction. Then what happens? Now this is the new position of the dipole, because I turned by 90 degrees, I said, do you remember? Turned by 90 degrees. Therefore this is the new position of the dipole. Plus Q minus Q, turned by 90 degrees. What is the change that happened? Watch the figure carefully. 90 degrees rotated, then earlier point P was axial point, now earlier axial line now becomes equatorial line. Can you see that? Earlier axial line now becomes equatorial. For what rotation? A rotation of 90 degrees. Otherwise, equatorial point becomes axial point. Right? Now this is P becoming equatorial point. But remember, since the distance is always taken from the center of the dipole, distance of a point from dipole is always from its center. Therefore, though axial point has become equatorial point, distance remains the same. Got the point? Axial point has become equatorial point, but distance no change. And yesterday's result we said, if R axial is equal to R equatorial, E at axial is 2 times E at equatorial point, or else now E at equatorial point becomes half of that at the axial point. Therefore, EQ is equal to EA by 2. Why? Axial becoming equatorial, no change in distance, and that is why it will be at 125 volt per meter at the right. Right? It becomes half. Now let us come to the potential point. Potential at the point P. Remember, yesterday we have told, in fact we have given expressions for potential due to dipole at axial and equatorial points. Use that now. Now since axial point has become equatorial point, refer your notes. At equatorial point, potential due to dipole is always 0, right? Therefore, axial point now in this case become equatorial point. Therefore, V at P, suppose if I write V at P dash, it becomes 0. When is this result occurring? When axial point is becoming equatorial point. Now, as a homework you can do, in the same example, if equatorial point becomes axial point, what will be the results? You please do it as a homework. Now, recollect the concept of potential energy. In the case of dipole planes in external electric field. Based on that, one simple example, you can see it on the board. Now, the question says, maximum potential energy of a dipole placed in an external field is, it gives a number 2 root 3 millijoule, 10 raised minus 3, right? 2 root 3 millijoule. Now the question is, find work done in rotating the dipole. Work done in rotating the dipole from equilibrium position to 60-degree position. Supposing this is the question. Now, brush up the concept of potential energy. It was U is equal to, with negative sign we are using, I have told you yesterday also, negative of P E cos theta, negative of P, dipole moment, E for external electric field strength, minus P E cos theta. Theta is the orientation of the dipole in the external field. Right? Now we have recollected all those things and a very beautiful figure as well. Now, U maximum also we have stated yesterday for theta equal to 180 unstable equilibrium becomes plus PE. Now, we use this for the data. Now, data says maximum potential energy. So, maximum potential is P. PE value is now given to be 2 root 3 into 10 power minus 2. So, that is how we are recollecting our concept. Now, one more expression that we have told yesterday, the work done, rotating, dipole, external field, remember? Negative of against torque, and hence we are using the negative sign. Negative of P times cos theta 1, theta 1 degree position to theta 2 degree position is rotated. Now I have substituted equilibrium position, theta 1, 0, cos 0, 1 I have taken, and the theta 2 degrees is given to be 60 degrees. Substitute cos 60 and you have the answer root 3 millijoule. Root 3 millijoule. Now the same another simple question can be, what is the maximum potential energy? Sorry, maximum potential is given. What is the maximum torque experienced by the dipole? Remember, torque P bar cross E bar, P is sin theta term. Maximum torque is equal to P times E. Therefore, the maximum potential energy, the magnitude, is same as the maximum torque experienced by the dipole. Now here theta 1 and theta 2 positions can be given any number. Like suppose it is rotated from stable equilibrium position to unstable equilibrium position. Right? What will be the result? Stable equilibrium theta 1 0, unstable equilibrium position means theta 2 is equal to 180 degrees. Likewise, concept of potential torque, potential energy and work done for a dipole placed in an electric field is a very popular CET model. I have done very few number of examples based on the concepts that we have discussed for the last 3 or 4 classes. And I have told you the very day one that every day you are receiving assignments as well on the same topics. We have a huge number of models covered. Huge number, again I'm telling you, every chapter we are covering as much as 100 plus models, which is more than sufficient preparation for our CET. So these are the few examples that we have done to rebrush all the concepts, and please do finish your assignments, and I do expect calls on your doubts clarification. Have a very good day. Thank you.